Good afternoon. Welcome to the webinar on the Geoscience methodology course for teachers. My name is Éva Hartai. I will lead the session today. And I'm a geologist and an honorary professor at the University of Miskolc in Hungary. I have 45 years of teaching experience in different branches of geology. Recently, I am the coordinator of the ENGIE project. The course, which is the theme of the recent webinar, was developed in the frame of this ENGIE project. We have 3 guests at the webinar, 3 outstanding geoscience experts who contributed to the course, and they will provide a short overview of their contribution. I would like to inform you that the webinar will be recorded, and the recorded video will be uploaded to the ENGIE YouTube channel. I also encourage you to submit questions using the questions and answers function in Zoom. And the questions will be answered after all presentations. Before starting the official part, I would like to invite you to reply 2 short polls. One poll is about your gender. This is what you can see now. And the other poll will be about your professional background. But first, I would like to vote in this poll. Please fill the 2 short polls because these are very important data for us when we assess the impact of our actions. So you can see the result now. Female-dominated webinar, which is very good. And then we can have the second poll. This is about your professional background. If you are a teacher, come from industry or the academic sector, please vote. Most of you are teachers, and this is good because this was our aim, to provide additional knowledge to teachers. So this was the 2 short polls, and thank you for filling them. Now I would like to provide a short overview of this methodology course. So first, I will share my screen. Before focusing on the course itself, first I would like to provide a few words about the project itself. So ENGIE comes from encouraging girls to study geosciences and engineering. This is an EU-funded project. There are 25 partners from 21 European countries. The main aim of the project is to raise the interest of young girls for geosciences, and by this approach, we would like to improve the gender balance in the field of these disciplines, because these are traditionally dominated by men. But of course, in the activities we organize for raising the interest, in these activities, boys can also participate. We do not want to exclude anyone. What kind of activities? A wide range of activities, like we organized already a video contest, and then there is an ongoing photo contest. We issue the ENGIE magazine, we organize science club events, webinars, field trips, workshops, conferences, publications, and this is our topic today. We also organize a course for science teachers. So what is the aim of this course? We would like to help teachers in teaching geosciences in secondary schools in an attractive way. The course will not provide a basic knowledge in geosciences. Rather, we focus on topics which are so-called hot topics. So the presentations and teaching materials are structured around 6 hot topics. This is climate change, geothermal energy, mineral raw materials, natural hazards, teaching methods for geosciences, and also the gender aspects. In each module, there is an introduction part, and you will find presentation videos and presentation slides. For the moment, we have 28 topics structured in 6 modules, but more topics will be added during the lifetime of the course. It will be open until the end of the project, which will be December 2022. The registered participants can use the materials which are in the course platform only for informational purposes and for teaching, of course. And they have to refer the course presenters. No certification will be provided because our aim is not to test the knowledge of the teachers. Rather, we would like to help them in teaching in an interesting and attractive way. So please register. This is the platform, and thank you for your attention. And I will pass the word to Tamás Miklóvicz, who is a project officer at the European Federation of Geologists, and it was Tamás who established this learning platform, and he will provide some details. So please, Tamás.
Thank you, Eva, for the introduction. So as Eva said, I will talk about more on the technicalities and about how you can access the content, how you can register, and what can you find once you already registered. So the ENGIE methodology course for science teachers is based on a Moodle platform. So this is open source, freely available, and easy to get started with. And how you can reach this, you can either find it on our website. There's a menu item here. It's called methodology course. You can click there and arrive to the platform. Or you can also go to the news section. We just published a news item about the methodology course for science teachers. So you can open here, you can go here, learn more about the platform, and open the link there as well. So without logging in, without registering, you can see the basics of the platform, but you cannot access the content. So you can read the introduction here. You can also see that this course is made out of 6 modules, as Eva said, about climate change, geothermal energy, mineral raw materials, natural hazards, teaching methods, and gender aspects. But for example, the keyword cloud will not result to any result because you are not logged in and you are not enrolled to those modules. So the first thing is to log in, or if you don't have, if you haven't had an account already, you need to register. And here I would like to ask a quick question from participants. If you already registered, raise your hand. You can do this in Zoom. Yeah, I can see that there are already there are 2 hands already. Good. Kiki, Silvia, Natalia, Kostas, very good. So if you haven't registered already, you can do so under this link. I just sent it on the chat. And the registration is quite basic. So you need to click here, create a new account. You first need to accept the legal notice. This is a standard legal notice that you can find in most of the website. What's important that if you don't want to share with us or with any of the other users your information, then please create anonymized username, anonymized name, no profile picture, and update the message preferences under edit profile, so the other user will not be able to access you. But we do not give out this information to third parties, so this is only processed internally. Once you agree, you need to create a username, password, email address, name, surname. So this is quite standard. Since I already have an account, I will quickly, actually have multiple accounts for demo purposes. I will log in quickly. And once you logged in, you will see that I can see some already online users. I can see Maria, Kiki already online. I could message them if I like to for networking. And since I'm already enrolled in all of these courses, if I use the keyword cloud, which is a good representation of what's inside these topics, for example, if I search for geothermal energy, I will find all the activities related to geothermal energy. So this is how the keyword cloud works on the website. So once we are in and we logged in, you can read the introduction about the course, but you can see this is the homepage. Then you have a dashboard, and then you can see the enrolled courses. So these are the three main areas that first you land on the homepage. You can go to the dashboard as well, where you see the recently accessed courses or course overview. And you can jump directly into one of the courses that you would like to. For example, I click on geothermal energy, and I'm already enrolled, so I can see the content. But let's say I quickly roll out from this, and I come to geothermal energy for the first time. I will see the introduction, but nothing else until I click on enroll. So this is important. We first need to enroll to a course naturally before accessing the content. So I click enroll. And here we are. So I can see in an introduction, this is the topics of the module introduction. Then there are three activities or three chapters in this module about geothermal energy. There's a short movie. There's original classification of geothermal energy, and then geothermal energy and its byproducts. So, for example, I click on the second activity, and the first chapter of that activity. So always there is an introduction about the presenter first, before the content itself. So this one is about Isabel Fernandez. Then I can click to next activity, and then I can find Isabel's presentation about the topic. So this is the YouTube link, it's embedded here. And this is an 18 or 19 minutes presentation about the origin and classification of geothermal energy. So here I can jump into the middle of the presentation if I like. I can scroll, and if I go to the next activity, I can see and download the slides Isabel used for her presentation. So I can scroll through the presentation slides here if I like, or I can open it in a big window, and I can download it from here to my downloads. But make sure if you use them, you need to make reference, as Eva said, that this is how these are available. So this is mostly the structure of all the subtopics inside the modules. So there's introduction about the presenter, there's the presentation as a video, and also the slides are available. And in some cases, the presentation is not available, or some cases the video is not available. But as Eva said, we are keep adding more and more content. So if you don't find this presentation, that might be added later on. Once you finished a subtopic, you can click on done. And if I go back to the overview of this module, I can see my progress here, completion progress. It says that I completed almost all subtopics except two. For example, I haven't completed this activity. I can click here. So this activity is only just an introduction about the presenter. And at the end of each of the modules, there's a forum which we encourage you to use. This is a classical forum, so you can add the new discussion topic that if something inspired you to talk about and share with the users, you can create a new discussion topic. Or you can jump into other discussions that are already present. For example, there's one discussion topic for each of the forums, which is about the feedback. So if you have any feedback, then you can share it. Was it interesting, or did you learn anything, or how did you find this topic? any feedback is welcome, and you can share it with us and with other users here. I'm quickly looking at my notes. So I think that's mostly how it is. You can get in touch to other users, so you can add them as contact. So I can see that Dragan already logged in. I can send a message, or I can add a contact. If you restricted your settings in terms of who can contact you, this you can do under message preferences. So if you don't want to be contacted, then select that my contacts only can contact you or anyone else on the site. So this is a user preference you need to look once you log in. So this is the online version. And what I can also show you is that there is also, as module, it's also available on a mobile platform. So I don't know if you can see my other screen, my mobile, that you can also access it on your iOS or Android device. You just only need to type in the address of the site, which is learn.engieproject.eu. So if I haven't made a typo here, there should be, yes. So this is ENGIE methodology course for science teacher. You can do your registration here, or you can already log in if you made your account already. So I already have an account, so I will log in here. And you can access the contact, all the content similarly as you can do it on the website. You find the introduction about the course, the keyword clouds, the online users, and also the available modules. So for example, I can complete and continue with mineral raw materials on my phone, and I can check the video presentations and the slides. If I finished with them, I can click on done and go to the next presentation slides, which I can open on my phone, and I can also download it once it's loaded. So you have the same functionality on your mobile application as you would have on the browser. So one last thing I wanted to show you, that here you can also, if you go to the modules, you can download the course. So this will download all the content, which warns in that is 35 megabytes, which is interesting if you are traveling or that you don't have internet access. You can just download it on your phone and access it on the go. So this is all from my side. So in conclusion, you can register your free account. Then you can enroll to a module of your interest. Then you can complete the activities which are presented. And the bonus conclusion is that you're very encouraged to spread the message. And if you want to contribute, I think you can contact Eva and contribute with your own presentation to the course. So thank you for your attention.
Thank you very much, Tomasz. Now, I would like to introduce you Paraskevi Nomikou, who contributed to the module on natural hazards with 2 lessons. Éva is a marine geologist who studies the morphology of underwater volcanoes with extensive experience in marine, volcanic, and seafloor extruding processes. She is an associate professor at the Department of Geology and Geoenvironment of National and Kapodistrian University of Athens in Greece. Éva has participated in more than 80 oceanographic cruises that focused on submarine volcanism, mud volcanoes, landslide and slope stability, and the exploration of seafloor mineral deposits. More recently, she has played a leading role in the evaluation of the potential hazards associated with renewed volcanic activity at Santorini volcano in Greece. Éva, please, the floor is yours.
Many thanks, Eva. Many thanks to all. Okay, let me share my screen. Okay, so thank you so much for the invitation. I found all these courses extremely interesting for the science teachers. So I'm going to present in a very short way about the very hot topic of volcanic hazards. So as we said before, we are going to present a very hot topic as volcanic hazards it is, as we have so many volcanic eruptions all around the world. So for the science teachers, this is a very nice topic, and of course the volcanoes shows a mystery to all the children, and of course it's a topic that you need to teach to the children. So as we say at the beginning, what is the volcano? Okay, so volcano is an opening in the Earth's crust through which lava, volcanic ash, and gases can escape. So volcanic eruptions are partly driven by pressure from dissolved gases, much as escaping gases force the cork out of a bottle of champagne. Most of the times the volcano are presented as a cone, a huge mountain, but we have also some other types of volcanoes. So what is below this volcano? Below the volcano, it is a huge tank, like a magmatic chamber. So it's a large pool of liquid rock beneath the surface of the Earth. And of course, all this magma wants to go to the surface through some cracks of the floor. So when magma is going out, it is named as lava. So lava is magma, is the liquid rock. Once it has been expelled from the interior of Earth with very high temperatures up to 1,200 Celsius. Okay, so the most characteristics of the volcano, the anatomy of the volcano, we have the magmatic chamber just below of the volcano. We have the vent, it's an opening, and the top of the vent, we have a crater. A crater is the mouth of the volcano. It's a circular depression that lava is coming out. And we have some other different types of characteristics. But where we can find volcanoes, for sure, we cannot find volcanoes in all over the world. So volcanoes are found in just a few areas of the world, most likely close to the boundaries. So you can see here the boundaries of the tectonic plates. And they are really great slabs of rocks that fit together like jaws to make an Earth surface. So we have three different types of environment that we can find volcanoes. The first environment is you find volcanoes in the convergent boundaries, okay, when you have the subduction zone. You have some other volcanoes just in the middle of mid-ocean ridges. And of course, we have some other volcanoes as hotspots like the Hawaiian volcanoes. But 75% or more than 75% of the volcanoes, the active volcanoes are located in the Pacific Ocean, as we say, the ring of fire. So in this area around Pacific, we have most of the volcanoes and we have also lots of earthquakes. But except of the volcanoes that we can find on land, as I am a marine geologist, you can find also lots of volcanoes on the seafloor. So most of them, about 75% of the world's active volcanoes are underwater. And the only sign that you can find a volcano, that a submarine volcano is being erupted, if you can see the ash that is coming out from the sea. So we have, as I said before, we have different types of the volcano, like one that we have a sealed volcano, like in Hawaii, the Mauna Loa. But the most impressive structure is when we have the caldera volcano. When we have the expression of the caldera, is a large basin-shaped volcanic depression with a diameter many times larger than induced volcanic vents. And of course, one common type of the volcano is the composite volcano. It's a stratovolcano, as it is composed by different strata of layers of lava and pyroclastic materials. Of course, we have different types of volcanic eruptions. One of the most catastrophic one is the Plinian eruption, and of course the Pelian eruption, but also we have the Icelandic eruption or the Hawaiian eruption. So how the magma, the lava, behaves when it reaches the surface depends on both its gas content and its chemical composition. Both of them are the very most characteristics in order to have a volcanic eruption. So lavas with very low silica contents have low viscosities and flow freely along any gas bubbles to escape readily, while lavas with high silica contents are more viscous, resistant to flow. So this is the most destructive eruption, like the Plinian eruption. And of course, here are some photos of different types of eruptions, like the allidic type of eruption. This is the eruption of the volcano in the Iceland during the summertime. This is the Hawaiian type of the eruption, where lava flows from the vent in a relatively gently low level eruption, so that people can evacuate the area around the volcano. We have also the Strombolian type, due to the stromboli, is the type of volcanic activity which produces frequent moderate eruptions. Of course, we have the Volcanian type, characterized by a dense cloud of fast latent gas exploding from the crater and rising high above the peak. This kind of eruption we had also in Santorini during the historical eruption of Santorini in Greece. Of course, the most destructive one is the Plinian type eruption. This is the intensely violent kind of volcanic eruption. And another very violent eruption is the Plinian type. What is an active volcano? So for us, for the scientists, an active volcano is the volcano that has been erupted during the last 10,000 years. These are some photos of a very active volcano like Vesuvius in Italy or Mount Etna. So all the scientists, due to the fact that there are some precursors and rest of the volcano, so we need to monitor the volcano, and of course, to include several types of observations like earthquakes, ground movement, volcanic gas, rock chemistry, water chemistry, remote satellite analysis. So all the scientists are focused to monitor the volcano in very different types like seismometers or GPS in order to avoid to have a huge volcanic catastrophe. This is, for example, some equipment that lots of people that they are monitor Etna volcano is used to monitor Etna, because Etna is one of the most active volcano in the Eastern Mediterranean Sea in general. So they have placed different types of instrument. And of course, the volcanic eruptions are one of the Earth's most dramatic and violent agents of change. So the most serious volcanic hazards are ash, are pyroclastic flows, the lava that is coming out, of course, earthquakes, fires, and of course, the tsunami. We will see. So the first volcanic hazard is the lava flows. Let's see also the lava flow that is coming out from the volcanic eruption of Iceland are streams of molten rock that pour out from an erupting vent. Lava is erupted during either non-explosive activity or explosive lava fountains. Okay, so it includes different types, several factors. The type of lava that erupted and the viscosity, the steepness of the ground over which it travels, the lava flows as a broadside or as between a channel, and the rate of lava production of the vent. This is the historical lava eruption in 1669 in Etna, that the lava flow was very close to Catania. This is the recent volcanic eruption that we have in Las Palmas. And as we all know, there are lots of fire from the lava that is coming out from a fissure, and lots of people have abandoned the whole place in La Palma. Another very catastrophic event is the pyroclastic flow. Pyroclastic flows is a dense, fast-moving flow of solidified lava pieces, volcanic ash, and hot gases. It occurs as a part of a certain volcanic eruption, but it's extremely hot, like 1000 Celsius, burning anything in its path, and it can have a speed as high as 200 meters per second. This is some impressive pictures, but very catastrophic ones from different types of eruption with the pyroclastic flows. Lahar is also another volcanic hazard. It's an Indonesian term that describes a very hot or cold mixtures of water and rock fragments that flows down the slopes of a volcano and typically enters a river valley. We had a very huge lahar when the Mount Helen in America erupted in 1980. And of course, one of the most dangerous volcanic hazards is the tephra, the ash. Okay, the volcanic ash is both easily converted upward with the plume and carried downward for very, very long distances. And as it falls out of the suspension, it can potentially affect communities and farmland across hundreds or even thousands of square kilometers. Here you can see the impact of the volcanic ash, impact of human health, on agriculture, on buildings, communication, generating facilities, in the whole life in specific area. Of course, gases. During eruption, volcanic gases like sulfur dioxide, hydrogen fluoride, hydrogen chloride, and hydrogen sulfide are emitted into the atmosphere, and they are very, very dangerous, not only for the people, but also for the animals. Here's an example of the eruption of Lake Nyos in Cameroon in 1986, and unfortunately, the gases are coming out during the night, and more than 1,700 people were killed automatically due to this gas releasing. Another volcanic hazard is tsunami, is the collapse of coastal or underwater volcano can cause a landslide that can trigger a tsunami. So tsunami is very, very common volcanic hazard when you have an island, and this island is a volcano. And of course, it depends where you are and how many days we have the volcanic eruption. As you can see, after the years, you can also have climate effects if the eruption continues more and more. Of course, the European countries have established, this is the worldwide, that you can find all the different types of dangers. And of course, in Europe, you have the catalog of volcanoes, the European catalog of volcanoes, that you can find lots of information, the volcanic information or the history of a volcano. Now, the scientists produce, in order to protect the people, they produce volcanic hazard maps. So if you are living in an island, for example, and the island is a volcano, you know in a place that if your place is very in danger if a volcanic eruption will occur. And of course, we have in the volcano observatories, we have volcano alerts, alert levels. Definitely alert level 5 is the one that you have at the big eruption, so everybody can leave the houses, can leave the place and go far away from the volcanoes. And of course, we have lots of leaflets for the people that they are living in the volcanic areas or the volcanic islands. They need to know what to do before the eruption, during the eruption, and after the eruption. So, for example, if you are going to visit Etna, all the villages around Etna, in the hotels, they have these types of different leaflets. And for us, the most active volcanoes, and this is my last slide, is Santorini. Santorini volcano, I think that is very, very famous for everybody about the Minoan eruption, the most catastrophic eruption in the last 10,000 years. For us, it's a huge caldera. This is the caldera that has been submerged, so we have water within the caldera. The main island is Styra, but we have also Nea Kameni and Palea Kameni. These are the new volcanic centers of the island. So the last eruption for Greece, the last eruption for Santorini is 1950. So in Nea Kameni, you can easily find and you can easily visit the new land, the newest land of Greece, of Europe in general. So thank you so much. So I will be here for any question.
Thank you, Evie. It was really impressive, a beautifully illustrated presentation, and I think that you managed to raise the interest of the participants for the natural hazards module. Now, I would like to introduce the next speaker, Kathryn Hadler. Kathryn is an engineer working in the space and terrestrial resources sectors. She is a lecturer in the Department of Earth Science and Engineering at Imperial College of London. Her field of expertise is mineral separations. She spent many years researching ways to optimize a critical process in the mining value chain called frost flotation. More recently, she has turned her attention to space and the production of usable resources on the moon. She would like to see the transfer of technology and ideas from space to transform mining on Earth. Kathryn, please start your presentation.
Hello, I think you can see my screen now. Yep.
Yes, perfect.
Super. Well, it's great to be invited to give a talk to you all. I'm going to give a quick 10-minute short version of the talk that I've recorded for the ENGIE methodology course, and it's on space resources. As Éva said, I'm an engineer and I spent many years looking at terrestrial mining, terrestrial resources. And in recent years, I've started focusing on space resources, and I think it's an absolutely brilliant topic to have a different discussion about resources, about where our resources come from, and where they might come from in the future, and how we use our resources. And that is the topic of my talk. So in my talk, you will find the following topics. We talk about human exploration beyond Earth, why we actually need to think about producing resources in space in the first place. It's also a great topic for talking about the need for resources. We can talk about planetary science. We don't necessarily cover that in my talk, but it is a great way to start the discussion around planetary science. But fundamentally, it's about sustainability of resource use, and I think that is absolutely critical. So in my talk, the following subjects are covered. We cover what are resources, what is space mining, what resources of interest are there on the moon specifically as our nearest neighbour. And then we focus very much on oxygen and water on the moon as the first thing that we're going out to space to look for. And then finally bring that, as I always do, back to Earth, because I think we're talking about space is great, but actually what we want to do is improve the way that we do things on Earth. And that's exactly what the focus is in my talk. So we use the focus of extracting oxygen on the moon as a way of thinking about resources. But just broadly, just to give you a feel for the kind of work that that I cover, the first question that we always have is, what is space mining? And space mining falls into two groups. There's the one where we say we can mine for materials that we can use in space. And the second way of thinking about space mining is mining for metals to bring to Earth. And it's the second one that gains all the attention. This is space mining that people think of. As soon as you mention space mining, people think about going and getting platinum from an asteroid and bringing it back to Earth and making billions of dollars. This is really what people think about as space mining. But actually, the first is the more likely. So in the first case, we can go up to the moon in the first instance and look for usable resources that will allow humankind to spend longer in space and travel onwards to Mars and beyond. So the things that we're interested in are things like oxygen, water, construction materials, so you can build habitation and shelter, and things that we can use for manufacturing. So if we can extract materials that we can then produce metals we can use for manufacturing. And this is really about the moon in the first instance. That's where we're going to go and demonstrate these concepts, and then onwards into Mars. It's often called SRU, which is space resource utilization, or ISRU, which is in situ resource utilization. So it's using resources found in space in such a way that it allows humankind to spend longer in space. And as I said, the second one is the one that everybody automatically thinks of, and that is the mining of metals to bring back to Earth, things like platinum, cobalt, anything that is of value from asteroids and other planets, so that we can reduce the impact of mining on Earth. That's a far more controversial subject, I think, but again, it leads to a discussion about resources, and I think that's always a great thing to be having, a great discussion to be having. So this is an image, this is a European Space Agency image of what a possible moon base might look like. And one of the great things about space resources as a subject is there are huge amounts of excellent images of what things might look like. Some of them are more science fiction than others, but it's a very creative subject, allows us to think creatively about the future. And in this image, we've got down at the bottom down here, we've got resource extraction. So this is where things like water ice might be extracted from a dark region. We've got fuel production. There's some astronauts for scale over here. And we've got construction using locally based materials, maybe by 3D printing or some kind of cementation process, and landing pads over here. But what this allows us to think about is actually what are the things that we need to provide for humankind to actually be sustained on the moon, and how do we make this sustainable? So let's think about our resources in a way that says, okay, we can build shelter from locally sourced materials, but how do we grow plants? Where do people live? All of these kind of questions that are fun, but ultimately very important. The other thing is that this is currently how the moon looks. Well, 50 years ago. So this is from one of the Apollo landings. And this is dry, dark, dusty, barren place. So to get from this environment to this environment requires a lot of infrastructure, requires a lot of planning. We need to think very carefully about the resources. Now, will this happen in the next 5 to 10 years? It seems relatively unlikely, but we'll see the first demonstration missions going off to the moon to demonstrate that we can extract usable resources in the next 5 to 10 years, and then onwards to bigger concentrations. So the types of resources that we have on the moon that might be of use, we've mentioned them already, things like water, ice and oxygen in the first instance. And oxygen is particularly important because it can allow humans to live, but also it's used for propellant. So if we can produce propellant on the surface of the moon, we can use that for refueling rockets, which means they can go onwards to Mars. And it also reduces the launch mass from Earth. Most of the launch mass currently to get rockets to orbit or to the moon is to get out the Earth's atmosphere. So if we can produce oxygen elsewhere, then we reduce that dependence. There's plenty of water ice on the moon. It's in the permanently shadowed regions. As these images show, there's loads of really lovely images that show where the water ice might be in those permanently shadowed regions. But there's not a lot we know about it at the moment. And so that's why NASA are heading there in their the next missions in the next couple of years. NASA will head to the lunar South Pole to try and characterize these lunar ice deposits more. We don't know anything about the form of the ice, exactly how it's mixed in with the dust that coats the surface of the moon. But also we need to think very different about the different conditions between Earth and the moon and how that might affect the material properties, but also how we might go about extracting resources. So we need to consider things like the fact there's no atmosphere. There are wild temperature swings. This is why we have those, and we have those permanently shadowed regions that are really very cold, have never seen sunlight. There is this dry, dusty layer called lunar soil or regolith that covers the surface of the moon. It's very abrasive. It sticks to everything. It will wear through equipment and machinery. There's 1/6 gravity, but also I think interestingly, absolutely no water. So whatever process we do on the moon, we have to do it completely dry. And on Earth, we have plenty of water available in which to process our materials. So we need to think carefully about how we do our processing. And this brings us back to Earth. We use, I say, huge amounts of water in mineral processing, which is really what my background is. But also that second on the two types of space mining, the second one is about providing resources so that we don't have to do mining on Earth. And I think the beauty of space resources is it leads us into this discussion around resources in general. And this is a copper mine high up in the Andes. It's a photo from years ago that I went there. You can see these trucks each carry 250 tons, so they're massive. It was a mountain, and they've kind of dug down and down and down and down. And this is one mine. There was 20 million tons of copper mined last year. The scale of mining is absolutely huge, and yet we need it, and we need more and more materials. And where does that come from? So we can have discussions around resource use. What resources do we use? Our resource use our consumption of resources has doubled in the next 100 years. It will continue to rise. And with the energy transition, and with the rise of electric vehicles, actually we start to need more and different types of resources. So an electric vehicle will take 4 times the mass of copper that a conventional car will. So actually, if we're going to convert all our vehicles to electric vehicles, we need to mine more copper, which is not necessarily as green as we think it is when you see those big holes in the ground. The other thing is we need different elements, because we're starting to use more of the periodic table in our technology, and same for things like solar panels and wind turbines. So actually there's a changing demand for resource, and there's a growing demand for resources, and we need to think about where that comes from. So just to finish off, the reasons that I think space mining is an excellent subject to talk about, I mean, I could literally talk about it all day, but the reason it's so such a good topic to talk about, it doesn't exist yet. like I said, we might see demonstration missions in the next 5 to 10 years, but at the moment it doesn't exist. And because of that, we can have a really interesting conversation about what does sustainability mean? What about resources? How do we use our resources sustainably? There's no wrong answers because it doesn't exist. So we can be creative about how we think about this. It allows us to think into the future. And for young people, I think that's really important. So it allows us, as I said, to think about our resources in a different approach. And it's really critical that we think about this and we talk about this with our young people, so we can develop solutions for the preservation of our planet and for other planetary bodies. Thank you very much. That's the end of my talk.
Thank you very much, Kathryn. It was really an excellent presentation and very convincing. I think that there will be a lot of visitors to your presentation in the learning platform. So thank you. And now I would like to introduce you Roberto Greco. Roberto is a naturalist who studies the teaching and learning process related to earth science education. He is an assistant professor at the Department of Science and Political Technology of the Institute of Geosciences of University of Campinas in Brazil. Here, Roberto coordinates the Geoscience and Society Research Group. He is also the chair of the International Geoscience Education Organization, shortly IGEO, and coordinates the organization of the International Earth Science Olympiad. Recently, he has been engaged in several projects where the focus is on the environmental perception of rural communities. Roberto, please, the floor is yours.
Thank you, Eva. Thank you for the invitation to participate to this webinar. It's a great honor. It's a pleasure to be here also with Kathryn and Eva. And I will share my screen. Please, if you could confirm if you are seeing, it's okay?
Yes,
okay.
Perfect.
Okay, so this is my short presentation. I would like basically to focus one aspect, the social aspect. That is an aspect that we really miss during this pandemic. And this is an aspect that teachers, even during normal conditions, sometimes suffer, because even if teaching is always in a social context, is often a solitary task, because not always the teacher have the possibility to be part of a community of teachers, to be part of a group, to could discuss, to prepare the lecture, to prepare the activity, and discuss the learning process. So in this my short presentation, I would like to stress this aspect, the social aspect, where a teacher can find some social support. And I will present some international association, like the International Geoscience Education Organization that I'm part of. And exists also an international commission inside the UGS, that is the International Union for Geological Society. That is the main international association, but there are many national associations. There are 2 strong associations in the United States with a lot of material, with journal dedicated on geoscience education, but there are many associations also in Europe. I put here the image and the link of the Spanish association, but we have association of teachers of natural science, geoscience, and biology, usually together in all the south of Europe, French, Portugal, and Italy. But we have also some associations, sometimes geography association in North Europe country. So I will really invite you, if you are not part of one of this community, to be to be in contact, because usually they share material, share idea, and it's nice to work together. And if in your country have not an association that take care of geoscience education, you can also consider to build one. I will now focus in IGEO, that is the association organization that I represent, just to give you an idea what we do. And basically, in IGEO, we try to promote geoscience education at international level, and to improve the geoscience education process, to provide material, idea, and to create this community and to the opportunity to people know each other and share idea. We have at the moment 115 countries that registered, that people from this country that register in our website, and is completely for free. And we provide a newsletter every 2-3 months. We have also a council with 47 countries represented, and we also create 2 regional chapters. And we would like to have in the future more regional chapters. At the moment is 1 in Europe and 1 in Latin America, but we also have the hope to have national chapter and more local chapter. The main activity are a conference that we held every 4 years. The next one will be next August in Japan, probably hybrid format. We will see about the situation. We have we manage the International Earth Science Olympiad since 2007, and this year and next year will be online, and next year will be Italy that will provide all the organization. And the International Science Olympiad is nice because give a lot of visibility to earth science education through the national competition, and also try to share a new idea on geoscience education. And then we have the international survey on geoscience education, usually every 6 years, that try to give an idea about the world situation. And well, you can find the result of the survey published as a scientific paper in the IGEO website, and unfortunately are not so so comfortable the situation of earth science education worldwide. So a lot is necessary to improve the situation, to give opportunity to young generation to have contact with earth science content. This is a map with the countries that are represented in the Council of IGEO. We still miss many countries in Europe. I stress Europe because this is a webinar organized by the European Federation Geologists, but you can see also other countries all over the world. And here I create a list with the member of the FG and the members that are now in the council of IGEO. So if you would like to candidate yourself to be representative of your country, you are welcome. And we have also the list of the countries that already participate to IGEO. So if your country is not yet participate in IGEO, why not think to have your national selection and participate to IGEO? Now I would like to give you 2 idea about what we develop as IGEO. During IGEO, in the International Earth Science Olympiad, we have several activity for the student, but like written test and normal test for get the medal. But we have also this special activity that is a cooperative activity where students work together. We make team usually in the presence situation with students from every different country, so mix for nationality, and we give a research question. And they need to go in the field. We bring them in a field, in a real field situation with a research question. and they have to collect data, usually with the support of some technical instrument, and they try and they need to create some hypothesis and to defend this hypothesis, and then to prepare a presentation and present the conclusion of their research to an international jury. So they pass through a real scientific process, and is a social activity, so they really enjoy this aspect, and is one of the activities that they learn more even years after the IGEO, after the IESO. And this is one of the activities that we would like to spread in the school all over the world. We recently published a paper on that in the FG journal. And then a really successful project that is the Earth Learning Idea, where you can download for free hundreds of really simple activity that the teacher can use in the classroom. You not necessarily need a laboratory, so they need really simple and cheap material. So it's really effective. It comes from the works of Chris King and his staff that they test this kind of activity for more than 30 years. So it's something that is really effective, and it works for school students and of different age, from primary to secondary school. And you find the PDF with all the description of the activity in a really simple way. Now there are also many videos that help to get the idea of the activity in a more fast way. And you find also translation in many different languages. So maybe you already meet the translation in your language. If you do not meet the translation in your language, you are welcome to join the project. It's a collaborative project, all made in a voluntary basis. You are invited for translating your own language, and it is possible to upload the translation in the main website. So these are the main activities that I would like to present. Thank you for your attention, and please, Eva.
Thank you, Roberto. It was really very interesting, and I think that you managed to raise the interest for IGEO and the Earth Learning Idea platform, and I think that we cannot compete that, but we can be some additional contribution. So thank you again, and now it's time to answer the questions, but as far as I can see, we have only one question. Although in the chat, the participants are very active, but actually one question: can we translate your materials to our language? Shortly, the answer is yes, because you know, we mentioned that these materials, which you can find on the learning platform, these materials can be used for teaching or for informational purposes. You can translate it, but please always refer the author and refer to the author and to the learning platform. So please indicate the link to the learning platform and the name of the author. So this is the only criterion, but otherwise you can translate it. I'm asking the colleagues who presented their topic if they agree with that. Roberto, Kathryn, I think that no problem with that. So if there are no other questions, we arrive at the end with the almost perfect timing. And first, I would like to thank our guests, Evie, Kathryn, Roberto for the excellent presentations, really engaging. And thanks also to the participants for their interest and active participation. And I would like to encourage you, the participants, to register to the course. And I hope that you will find it useful and the teacher colleagues will benefit from the content of the course. So again, thank you for your participation and have a nice evening. Oh, sorry, before we close, I have just realized that there is one more question. Question to Kathryn. Mining outside Earth implies the concentration phase to be to be done before taking products to our planet. I'm sorry, but the question is not completely clear for me.
It's all right. I think I know what I think I know what Prestigious is asking. You know what? There's no right answer to that. Do we? It's an excellent question. Do we do our concentration? Where do we do it? So if you want to harness, let's say, platinum from an asteroid, which is obviously where people see dollars, do you bring everything back to Earth or back to your moon base or back to Mars and process it there? Where do you actually do the processing to get the materials and bring it back to Earth? And actually, there is we don't know. The whole field is. It's very far away from thinking about that, but that's exactly the kind of question that needs to be asked. So it is a great question to ask.
Okay, thank you. Thank you for your answer, Kathryn. And I think that we are really at the end now. So again, thanks for your participation. Thanks for your presentations. And I close the session.
Thank you so much. Thanks.